All right, guys, welcome back. We're going to continue our discussion about BGP here. And actually, we've already kind of talked about what we're talking about today, but we're going to get into a lot more detail in this case. We're going to be talking about BGP route reflectors and configuring BGP route reflectors. It's not a difficult thing to configure, but there are a lot of considerations to take into account, especially with how routing is performed. And that's really what we're going to take a look at. The actual configuration of route reflectors is actually a very straightforward process, but we're going to talk about the BGP cluster ID, specifically how it works, how it's going to influence the advertisements of our routing updates. But we're going to see that the big thing to understand about route reflection, specifically the route reflection configuration, is that the route reflection configuration is going to be primarily based on what our underlying topology looks like, specifically with how routes get advertised, how we see redundant paths, and so on. I'm going to try and demonstrate a lot of these concepts in tonight's lesson. As the route reflector is going to process updates, it's going to do that differently depending on what type of neighbor it came from. And this is something that we talked about in our previous lesson, is the route reflector advertisement of prefixes is going to be based on the physical topology. So for example, if I learn an iBGP route coming into a route reflector, let's say for example, if I look at my topology here, let's say, for example, I've configured router 5 as a route reflector in this topology. If I learn about, here, let me do this. Let me grab a snippet here of this topology. So if I learn about a route via an iBGP peer, and this router has both clients and non-clients configured in the autonomous system, those are all clients of that route reflector, that iBGP route is going to be passed over to those clients. All right. Now, if say router 2 was another route reflector and it was configured as a non-client, meaning that we're not actually reflecting routes to that peer, but we do have a peering relationship, I will send that information over to that non-client as well, because the route came in from an iBGP peer. Additionally, if I had other iBGP peers, I would forward that route over to those other iBGP peers. So essentially, a iBGP route that comes into a route reflector client is going to get propagated to all of its clients, all of the non-clients, as well as other iBGP peers. Client routes that get learned also get passed to iBGP peers, other clients, and non-clients as well. It's only the non-client learned routes that do not get passed to other non-client routers. So non-client learned routes will get passed to iBGP peers as well as other clients, but it will not get passed to other non-clients. We'll take a look at that. I'm going to start by configuring the topology here with just a single route reflector. We'll talk about the design considerations when we're dealing with multiple route reflectors, and where we decide to place route reflectors based on these particular rules. So we're going to take a look at a couple of examples where we place the route reflector. One is going to include placing the route reflector in the data plane path, and then we're going to take a look at an example where we kind of look at a central point of aggregation, in this case router 4, where the route reflector is not necessarily in the data plane path from the perspective of other routers. For example, if router 1 here is acting as a route reflector client to router 4, being the route reflector, reaching this 8.8.8.8 prefix on router 8 doesn't necessarily mean that the route reflector has to be in that data plane path. In this case, it wouldn't even be a reflected route back to router 1, because router 1 has an iBGP route and it's always going to prefer an iBGP route over an iBGP route. But we might see the same scenario if we're talking about router 2. So we're going to take a look at that from a configuration standpoint. We're also going to kind of analyze how it affects the route selection process, even if we try to modify the route selection or path selection process by modifying the attributes of the path, the routes themselves. All right. We're also going to take a look at the difference of the configuring this per address family. I'm probably not going to get into the actual configuration of address families because we're going to do that a little bit later on when we look at multi-protocol BGP. But keep in mind, route reflector configurations are done per address family, and having a route reflector in IPv6 unicast does not necessarily mean that you have to be a route reflector for IPv4 unicast. All right. Now the configuration itself is going to be pretty straightforward. We just go under the BGP process and we specify from the route reflector's point of view who the clients are. So we specify the client peers using a neighbor route reflector client command, which I'll show you guys a little bit later on. From the client's perspective, there's really no different configuration. We do have to set up our peering relationship with the route reflector, but it looks just like a normal iBGP peering relationship. Remember, the ultimate goal here is to get rid of the need of having a full mesh full iBGP mesh in our domain. So if I wasn't using a route reflector in this AS100, or I wasn't using confederations in the AS100, every one of these clients or every one of these iBGP peers would have to have peering relationships with each other in order to ensure that we're passing all of the network layer reachability information across the domain. I probably missed a couple there, but you get the idea. There has to be a lot of individual peering relationships that have to be established, and it gets a little bit complicated. But if I go ahead and configure router 4 as a route reflector, the only peering relationships that we have to have are those there. It's very much like a designated router in OSPF on a multi-access segment. There is a trade-off though. We're reducing the complexity of the control plane, reducing the number of routes that we have to have in the control plane, but we're also still losing visibility in the domain itself. I'm going to try and demonstrate that concept to you guys as well as part of this process, to where we lose network layer reachability information, well, specifically redundant route information by using a route reflector. I'll try to demonstrate that. Okay. We specify that the router is or is not a route reflector for processes. We're going to use it in the global BGP process for IPv4. But if we were running different AFIs or SAFIs for IPv4 unicast or VPN v4 unicast, different address families, that configuration doesn't go under the global BGP process. That configuration goes under the address family configuration for whichever address family information or SAFI we need to configure. All right. Again, we're not going to look at that from a configuration standpoint in this lesson. We'll look at that in a different lesson. Okay. The client does not need to specify the route reflector is a route reflector. It doesn't negotiate those attributes in the BGP process. We just need to configure the route reflector components on one side. And we'll take a look at that. So I did modify this configuration a little bit from our previous BGP example. So what I'd like to do prior to getting into configuring the route reflectors, I'd like to go ahead and get some of the basic BGP configurations done in this topology based on some of the changes, and make sure that we have essentially our standard full mesh iBGP configuration done. We're going to use our BGP peer groups to do that. We pretty much have that configured. We just have to enable some interfaces here. So I'm going to pause the video real quick and just kind of run through the config and make sure that we have everything configured correctly. All right, so I've gone through and I've kind of modified the configuration a little bit here. Let's just do a sanity check and kind of go through and see what we expect to see. I've done a full iBGP mesh inside of AS100 because I want to be able to take a look at this and compare it and contrast it to what we're going to see when we're running a route reflector. Okay, we're going to end up configuring router 4 as a route reflector. So we will be stripping off the configuration a little bit on these router 2, router 1, router 3, and router 5. But it's nice to know where we're coming from before we get into where we're going to, because we want to see the effect or the impact, if you will, on the routing decisions and the routing process based on these changes. So we should see, from router 2's perspective, we should see several different peers. Let's go back to router 2. And let's do a show IP BGP summary. And we should have a peering relationship with router 1, with router 3, with router 4, and router 5. So that looks good. We are getting prefixes from these routers. Router 5 did not come up. We're going to have to figure out why router 5 did not come up. Oh, I know why router 5 did not come up. Remember, BGP doesn't have its own transport. And router 5 we added to our autonomous system number 100, and we're using eIGRP as our transport, but we didn't configure eIGRP on router 5. So let's do a section eIGRP, and we'll drop that into router 5. That should fix that problem with router 5. All right. So let's go ahead and copy this and go over to router 5 and paste that in. All right. So we should form an adjacency with router number 4. And now when I go to router 2, I should see that I have the ability to communicate to that peer. I have reachability. Recursion is possible, in other words. Let me try and ping 5.5.5.5 source 2.2.2.2. Should be able to reach it. Okay, why not? We may just not be converged yet. Let's check router 5 again. We do have an adjacency, show IP eIGRP neighbor. So we do have an adjacency. And router 4 should have several adjacencies. Show IP eIGRP neighbor. Router 4 has an adjacency with router 2 and router 5. That's correct. Actually, router 4 is missing an adjacency with router 3 and with router 3. So let's troubleshoot that. We might have some interfaces that are down. Yep, there we go. Interface gig 03, no shut. And let's do the same thing on router 2. Show IP interface brief. Yeah, we're good there. Do show IP interface brief. This kind of does speak a little bit to the troubleshooting piece, because you want to make sure. I noticed that the connection between router 2 and router 5 was idle when I was doing a show IP BGP summary, and immediately I'm thinking, okay, do I have a recursive way of reaching router 5? Because the iBGP transport doesn't exist, or BGP transport doesn't exist. We have to rely on the underlying IGP to be able to reach router 5 to be able to form that adjacency. So it is important to be able to establish that. Let's do a show IP eIGRP neighbors now and see router 2, router 5, and router 3. That looks better. All right. So router 4 should have an eIGRP adjacency to these 3 routers. So it looks like we're good to go now. Let's go ahead and go back to router 2 and just verify reachability. Well, we can do a show IP BGP summary just to check real quick. So it still looks like we're having some sort of issue getting to router 5 in this case. So let me do a show IP route pipe include D. And we do not have reachability to 5.5.5.5. Looks like we have reachability to the segment 45, but we're trying to peer to the loopbacks in BGP, And if I can't recurse to 5.5.5.5, I'm not going to be able to establish an adjacency through BGP with 5.5.5.5. So let's do show IP interface brief, make sure we have the loopback. It is assigned, it is up, show run, pipe section router. And let's make sure it's part of the EIGRP process. It is not. I just remembered. When I pasted in that EIGRP address family configuration, I did not include loopback 5.5.5.5. So that's an easy solution. Config T. But see, these are the kinds of things, I'm not going to say I did it on purpose, but these are definitely the kinds of things that you need to consider when you're troubleshooting on the test. And you have to be able to do this quickly, right? And understanding essentially how BGP forms these adjacencies and what it's looking for to be able to establish the adjacency is really important, all right? There has to be underlying transport for us to be able to reach that particular destination. So we reset our neighbor. Now I should have 5.5.5.5, which means I should now see that yep, there's my neighbor is up, show IP BGP summary. All right, so we do have a full mesh. We've established a full mesh with all the peers in this topology. You can see that they do have different views of the topology. Even though they're all sharing prefix information, the number of prefixes that we're receiving does indicate that they do have different views of the topology. That will not synchronize. It just happens to be based on loop prevention mechanisms in BGP. You know, iBGP peers not sending other information to other iBGP peers. But let's take a look at reachability here from the perspective of maybe reaching this 8.8.8.8 subnet and the 7.7.7.7 subnet, which are external prefixes. Okay, so if I go to router 2 as an example, and I do a show IP BGP 2.2.2.2, I can see that I'm actually learning about that prefix from multiple sources. I'm learning about that prefix from, oops, I don't want 2.2.2.2, I want 8.8.8.8, sorry. Thought that was too many. 2.2.2.2, that makes sense because that's the loopback on router 2, which is part of BGP. We can talk about this in a little bit, but I'm focusing on those external routes presently. So you'll notice here that we are routing to this destination, and we're going through AS51 first and then to AS50. We're not advertising this prefix to any peer, which makes sense because we're an internal BGP router. And we would have learned this prefix from other iBGP peers, which means that we're not allowed to propagate that prefix onto other iBGP peers. Again, the whole purpose of going through this process is to see the difference between a full mesh operation and then what is going to happen when we're not operating in a full mesh and we're using route reflectors. All right, now I should be seeing, so we're going to 51 and then 50. So I am getting the prefix from router 5. It's coming in as an iBGP route. That's the origin is IGP. It is a valid route. It is the internal route, the best route. But let me see if we're actually seeing that particular prefix of it coming in from router 8 as well. So it looks like we're only learning about this prefix from router 5. And that's a little surprising to me. And the reason why that's a little surprising to me is because it makes sense to go to router 5 for the 7777 prefix. It doesn't make sense to go to router 5 for the 8888 prefix because one of the major attributes that we use to choose which path we're going to take is the AS path attribute, or the AS length, which this has a length of 1, this has a length of 2. If I look at the topology, router 2 should really be egressing from router 1 to reach this 8.8.8.8 prefix. So I need to verify this eBGP peering relationship here, and I need to make sure that router 8 and router 1 are peers, because it looks like we're not learning that prefix. So iBGP summary from that router. Yeah, so we've got an idle state with router 8. So I'm not doing this intentionally, of course, but it is kind of a good exercise to say, you know what, the network is not really behaving the way I expect it to behave based on what my understanding of BGP is, and that is that router 2 should not be going to router 5 because there's a shorter AS path to get to that 8.8.8 network. So question is, why am I not peered with router 8? Let's do a show run pipe section BGP. Most likely it's an interface that's shut down. Let's go over to router 8 too, because we do have the peers established, the neighbor of 172.16.18.8, show IP interface brief. All of our interfaces are up. The 18.1 interface is up. So let's go to router 8, do show IP interface brief, and the interface is shut down. All right, so interface gig 03, no shut. All right. Now I think we might be clean. We'll be able to tell from router 2's perspective because router 2, the route should get added to the database, and router 2 should make a different decision on how to reach that particular destination now. Let's see here. Yeah, so now it's going to router 1. All right. So it's made a decision to go to router 1, shortest AS path. If I do a show IP BGP for 8.8.8.8, I can see that, yeah, it is coming from router 1. It's still originating through iBGP, and we're still not advertising it to the peer, but that's okay. All right, so it does look like we're kind of behaving normally. All right. What we want to do, though, is we want to clean this up a little bit because we have so many peering relationships. And we are learning about all these different loopbacks from all of our different peers. Some of these routes are being used. This is the 2.2.2.2 is locally originated on router 2. This loopback here, 1.1.1.1, we're going to go to 12.1, which is router 1, to reach that particular destination and so on. But as you can see, the control plane is rather complicated. And that's what I want to point out here, is that we've got all of these different entries in our BGP database, and you can extrapolate this to, say, a much, much larger network where you potentially have 100,000 routes or 200,000 routes or 500,000 routes, and it gets a little bit more complicated. All right. So far we do have reachability. I should be able to ping 7.7.7.7, source that from 2.2.2.2. I should be able to ping 172.16.78.7 and source that from 2.2.2.2. So I can reach pretty much all the destinations in the topology. We don't have time to get into specific routing decisions at this point. We're going to get into our configuration of route reflectors. Okay. So that's our topology. We're going to configure router 4 as the route reflector in our first example. We have 3 ASs like we always had before, AS50, AS51, and AS100. Previously, or as it is right now, we're running a full mesh of peerings. So let's go ahead and remove that. And instead, in AS100, everybody is going to peer with just router 4. So let's go ahead and make sorry about that, the battery's died on my microphone. So we're going to be, rather than peering with all the routers within the autonomous system, we're only going to be sending our information to router 4, and then router 4 is going to be responsible for essentially reflecting all of that reachability information back to all of the other routers. Now, in some cases, router 4 will be part of the data plane, and in some cases, router 4 will not be part of the data plane. For example, router 1 will not go to router 4 to reach the 8.8.8.8 subnet, but it will have to obviously go through router 4 if it wants to reach the 7.7.7.7 network. All right, and our decision process on how we decide to route to a particular prefix is not going to change. We will have lessons on that specific BGP path selection process later on. That's not going to change, but how we learn the network layer reachability information is going to change. All right, so we're going to start on all the perimeter routers. We're going to remove our iBGP. We're going to leave the external peerings in place. And then we're going to set up on router 1, router 2, router 3, and router 5. We're going to set those up as clients to router 4 as a route reflector. So let's just verify this configuration one more time. Take out BGP 100. Well, on router 5, we're not going to... Let me grab one more thing from router 5 and router 1 because we're going to need those external peerings in there. I'll do router 5 and router 1 separately because I don't want to remove the eBGP peering relationships. I only want to remove the iBGP peering relationships. So let's go ahead and paste in this configuration on router 2 and router 3. And then we'll take a look at router 1 and router 5. All right. So we'll go over to router 2 and router 3. And paste this config in. Okay. All right. It's running a little slow today. Sorry about that. So we see the adjacency with router 4 come up. That makes sense. Right now, we've essentially broken BGP because we haven't configured router 4 as a route reflector. We've just doing standard peering relationships with router 4. So we're losing some network layer reachability here, but that's to be expected as we're doing this migration. Okay, let me go to router 1, 2 at the same time and show run pipe section BGP. And just grab the piece that I need to keep for the external relationship, which is right here. I'll get there eventually. All right. All right, so we can paste this into router 1. I mean, I don't know if you guys have any questions about what we're doing. I think it's pretty clear. We're just getting rid of the full mesh. And we're going to look at how BGP reacts when we're using a route reflector, how the information looks in the database, and take a look at some of the caveats when we're dealing with route reflector with regard to how we're actually sending in the information. All right. All right. So the first thing I want to verify is make sure I haven't lost my external peering relationship. That should come back up. So we've got our external peering relationship, and we do have our peering relationship with router 4, getting those 13 prefixes from router 4. If I go to router 1, show IP BGP, I see that I have, summary. I see that I have my peering relationship with router 4, and I've got my external peering relationship. Now, without configuring router 4 as a route reflector, you can see that from the perspective of router 2, we've lost reachability to the 8.8.8.8 prefix, and we've lost reachability to the 7.7, all the external networks essentially. All we're getting is all the internal networks and some of the networks that we're learning through eIGRP. That's why we got the rib failures on for the .18, the .13, the .12, and so on, because those are all prefixes that we're learning through our IGP process. All right, but let's go ahead and set up router 4 now as our central reflector so that we can advertise those external prefixes through the rest of the domain. All right. Now we could do this with individual neighbor statements. We could use peer templates or peer groups. In most cases, you're going to use a peer template or a peer group so that you can modify policies more effectively, and that's why I try to focus on utilizing these peer group configurations. Even though I only had really one peer, one peer between all the other routers in router 4, I may want to use those peer group policies to create other peering relationships with other route reflectors in the domain and so on. So in most cases, we're probably going to use peer templates or peer groups. So be very familiar with that when it comes to the exam, because within the scope of the exam, they might have peer groups or peer templates configured, and you need to be familiar with how to read those and so on. All right. In this case, we're going to use a template because it's just going to make things much, much simpler. So let's go into router 4, and let's do a no router BGP 100 and just get rid of the entire configuration. Okay, and start over. So we're going to do a router BGP 100, and we're going to do a neighbor. And in this case, let's create a peer group called RR clients, and we'll apply all of our peering properties to that particular peer group. So neighbor RR underscore clients, we're going to say remote AS is 100. We're going to say that the update source is loopback 0. Loopback 0. And we're going to say the most important one is that we're going to specify that all of the neighbors that we specify with this particular peer group are going to be route reflector clients. Okay, and then we just simply have to set up all the peers with all the neighbors. So let's do a neighbor. I wish you could use wildcards in this case, but can't. Peer group are our clients. By the way, the peer group names are case sensitive, so you do need to make sure that you appropriately configure the peer group name. And let's do 3.3.3.3. And 5.5.5.5. All right. Again, we've already assumed that we've gone through, we've tested the transport between the neighbors. And again, in our topology, we're using eIGRP for our IGP transport between the neighbors. If there is no IGP reachability, and we saw that in the beginning of this lesson where we couldn't peer with router 5, it's not going to work. You need to have that transport because iBGP doesn't have its own transport. So let's do a show IP BGP summary. And make sure that we have our peering relationships with each of our routers. 1, 2, 3, and 5. I think that's all of them. 1, 2, 3, and 5. Yep, that's correct. Okay. Now, obviously, now that we know that we are peering, we see peering relationships. We're not learning any updates. Well, we are actually learning updates from these peers because of their relationship with router 4 as a route reflector. The difference here is is how we learn about the eBGP routes from router 1, right? So for example, the 8.8.8.8 route that router 2 didn't have before, router 1 is going to send that route to router 4, and then router 4 should reflect that route back to all of the other neighbors. So if I go to router 2 and I do a show iBGP, I should now see those external prefixes with reachability to those particular destinations. I'm still making routing decisions based on standard path selection processes, right? So I'm still going to go to router 7 to reach 7.7.7.7, and I'm going to go to router 8 to reach 8.8.8.8. But look at the next hop value that's being advertised with these particular prefixes. It's no longer router 1 who originates the eBGP route into iBGP, and it's no longer router 5 who originates the eBGP route into iBGP. Let me see if I have that still in the screen here. Let's see. Yeah, right here. Right. This is before we fixed router 8. The next hop attribute was the edge router that was originating that route. So the interesting thing about this concept is that the route reflector maintains next hop attributes and maintains other attributes that are established at the perimeter because the route reflector does not need to be in the data plane path. Now, in the case of 7.7.7.7, if I do a trace route to 7777 and I source that from 2222, I can see that router 4 is in the data plane in this particular case. And that's just simply because of the physical topology. Again, that's a consideration that you have to take into account. If I do a trace route to 8.8.8.8 and I source that from 2.2.2.2, router 4 is not in the data plane in this case. So even though we're able to disseminate the network layer reachability information, just because we're a route reflector, we're not inserting ourselves into the data plane path. Okay? So router 4 is not modifying the attributes in the updates. And the reason that is because it could potentially cause a loop in the data plane if R1 was advertising the route to R4 and then R4 was advertising a route to R2 and it sets the next hop to itself. That means the traffic would go from R2 to R4, and then it's possible that R4 would end up sending that traffic back to R2. That's why we don't want the route reflector to be part of the data plane. Now, our decision to where we place the route reflector could be based on the physical topology, but in most cases, it's just a control plane box that you have TCP reachability to, and then based on your next hop value and your IGP recursive reachability to that next hop, that's how you're actually going to leave the network. And that's what we're seeing in this particular case. All right. So if we look at this from R2's point of view, the key difference from the iBGP full mesh design is we only learn about the route from one path to every destination as well. Let me do that again. Show iBGP. There is a slight exception to that rule, but I'm only technically learning about one path. Show iBGP. So you can see for the external paths, the 7777 and 8888, and the 172.16.78 network, I'm only learning about one path. Now, granted, for the loopbacks, I'm learning about those a couple of different ways, but that's because of what we're doing with our IGP protocol and BGP. You can see that there are metrics applied in some cases. There are metrics not applied in some cases. So we'll leave those to the side for now. But that's one of the actual disadvantages of using a route reflection, right? the route reflector learns all of the updates from all the clients. What happens then is that the route reflector makes its own best path selection based on what routes are actually used based on that best path algorithm. We choose the route, and then that is the route that ends up getting advertised to the reflector clients. So rather than advertising full network layer reachability, we're only advertising the best path. Now, the route reflector is choosing that best path based on standard BGP principles and standard BGP path selection processes. So it does mean, though, that router 4 controls whether the traffic egresses via router 5 or via router 1. All right. Now we can see this actually on the reflector itself. Let's look specifically at the external BGP routes on a route reflector. Show IP BGP. Let's do a regex that begins with 0 through 9 and contains any number of those values. All right. So this is showing us all of our external prefixes. Okay. And let's look at the route specifically from router 8, which is the 8.8.8.8. So this prefix is coming in from router 8. It's going over to router 1. And then router 1 is advertising it to our reflector, which is us, router 4. All right. The reflector is choosing that particular path as the best route, and that's what it's advertising to everyone else. Now, technically, it does also advertise it back to router 1, being that router 1 is a route reflector client. There is no notion of split horizon in BGP. So let's see what router 1 does with this information, because we don't really want router 4 creating a loop by continually re-advertising a route to router 1 that router 1 is originating. So let's do a, let me think, let's do a Debug Ip Bgp Updates. Hopefully I'll be able to show you this. And we want to basically try to refresh the routes. We'll have to clear iBGP star here, and let's do the same thing on router 4. Clear iBGP star. Just kind of refresh everything, because there's one specific thing that I want to show you, and it has to do with Originator Id. There are two components within route reflector configuration that allow us to identify whether or not we're receiving information that we're originating. And one of those is called the Originator ID. The other is called the Cluster ID. I'll show you the Cluster ID towards the end of the lesson here. We have a question from Mike. For the BGP regex, do the exclamation and the $sign have a different meaning than standard regex? No, they do not. I mean, not the exclamation, the circumflex. The circumflex means that it begins with a certain value, right? But as far as regular expressions go, BGP regular expressions use the same wildcards, the same options as any other regular expression that you might use for like voice over IP and so on. So let's see, Mike says, so it's regex on a certain field. I'm not sure what that means.
Okay, so if you scroll up a little bit.
Yep. Oh, yeah. I know what you're saying. Yeah. So yes, in this particular case, yeah, Mike, you weren't in the other lesson where we did that. This is looking specifically for AS path. So we're essentially...
Okay, so it only looks underneath the path.
Yes, so this applies to the path.
If you wanted to find anyone that began with a path 51, you could put just caret 51 and then plus, and then that would
Yes, correct. That is correct. In this case, we're just basically saying any path that has a number, because a path that doesn't have a number is internal BGP. So we're trying to pull out all the external paths or external routes from the
Gotcha.
database.
Because I was looking at that, and obviously I know that begins with a number, but obviously that output does not begin with a number. So it was on the field. Okay, I'm good.
Yeah, so that's why these were excluded, because they didn't have a number in that field. And that's a little confusing, right? Because you're not necessarily applying the regular expression to that particular value, but that's actually inferred based on standard BGP regular expression rules. All right, there's some other little tricks and tricks to the trade, but that's one of the ones that we tend to use quite a bit. Okay. All right, now let's go back to router 1, and I'm hoping I'll see this in router 1. Yeah, there it is. So we received an update. Let's go to, this is what we're looking at. So I was looking specifically for 8.8.8.8, but I guess it doesn't really matter. What we're actually looking for here is why certain updates are denied. So let me see, go back to the beginning. All right, that's good. Denied due to AS path contains our own AS, so that's a loop prevention mechanism for iBGP. But what we're looking at for the route reflection is specifically, this is where we're advertising the prefix to the route reflector, and this is where let's go down to here. So it was kind of at the bottom. This is where we're receiving the update, and it's denied due to the originator is us. All right. So basically what this is saying is that we're denying this particular update because the originator ID contains my own router ID. The originator ID is always going to be based on the client's router ID. All right. And this is, again, denied due to next hop is our own address. So in this case, I'm denying this because I'm going to prefer, not only is it originated by us, there's a couple reasons why this was denied, but I'm going to prefer a quad 0 next hop as opposed to a different next hop for what we call local routes, or routes that are originated by us. All right, so these are some of the rules that we're going to get into later on with regard to path selection and so on. But the main reason I wanted to kind of point this out was because we are, this is the one actually that I was specifically looking for, originator is us, is this loop avoidance mechanism that's built into route reflection configuration. I do send the route to router 4, but because there's no split horizon rule, router 4 is going to send the route back to me, and I'm going to basically deny that because that's our loop prevention mechanism. Yeah, I'm the one that originated the route. The originator ID is my router ID. Well, I'll show you how we can see that actual value a little bit later on. So in this case, R1 is sending a route to R4. R4 is sending it back, and that's because R4 happens to choose that as the best path based on the AS path attribute. But when R1 gets it back, it says the originator ID is 1.1.1.1, which happens to be the router ID of router 1. That's my router ID. And it knows not to accept that particular update. All right. Now, this could be like any other troubleshooting case you'd like to see in, like, say, external EIGRP or some other IGP. If two routers have the same router ID and they were advertising their routes through a reflector, they wouldn't be able to accept each other's updates because they would have the same originator ID. So it's really just like any other protocol, and just like in every practical case, the first thing that you should do when you're actually turning on the BGP process is to set the router ID to some sort of static value, If you remember, router ID selection process for pretty much every protocol is the same. We use the highest, well, actually we use the manually configured router ID first. If that's not set, we use the highest active loopback, and if that's not, if there is no loopback, then we use the highest active physical IP. We haven't set any router IDs manually, so all the router IDs are going to be the loopback interfaces that we have in this particular topology. All right, the updates are looping. They are looping back and forth, but it's not an infinite loop. So there is a process where everything kind of calms down and we identify based on the originator and so on. So eventually they do get discarded when we see that the originator, or they would also get discarded, and I'll see if I can demonstrate this towards the end of our lesson, is the cluster ID, right? If I'm a route reflector and I see my own cluster ID in the list for routes that are being reflected back to me from another route reflector that happens to have the same cluster ID, which you can do for redundancy, I'm going to go ahead and ignore that because I see that in my own cluster list. Now what I want to show you with clearing the table is that there is an interesting scenario where we can get into, all right? Let's see from router 2 that we can actually reach these external destinations. So I'm going to ping, I think we already did this, but I'll do it again just because we're going to be making a couple of changes here. So let's do a ping to 7.7.7.7 and source that from 2.2.2.2. And let's do a ping to 8.8.8.8 and source that from 2.2.2.2. So we have reachability. Now let's do a trace route, which we also did before, but I just want to do it one more time. Trace to 8.8.8.8, source that from 2.2.2.2, and also 7.7.7.7, source that from 2.2.2.2. So again, we talked about this, we're going to AS 50. For 8.8.8.8. I'm not sure why the AS is not being reported there, but we're going to AS 50 from 8.8 for 8.8.8.8, and we're going to AS 51 for 7.7.7.7. Okay, and those are optimal paths. Even though the route reflector was the one that originated those routes, technically, because they were reflected back to router 2 from router 5 and router 1 respectively, we're choosing the best path. All right. To get to 7.7.7.7, we go directly to AS51. What I'm going to do is make a different change to make those external paths look kind of like one another. Well, I may not. Let me see if I try to think how I want to demonstrate this. Let's say that on router 8, I'm going to take my own updates and I'm going to prepend it out once, and then on router 7, actually, yeah, router 7, I'll do the same thing so that we have the same AS path link. Thinking about this, I'm trying to think if that's the easiest way to do this. There might be actually an easier way to do this. Yeah, there is, now that I think about it. This is a little bit complicated to try to demonstrate. When I was trying to put together my notes, I was thinking about maybe even trying to do this in advance, but I didn't. So we'll see if this works. But the reason why I'm even talking about this is there's an interesting case we can get into with route reflectors, where the convergence of the network will determine which egress path we choose based on not BGP path selection rules, but based on the order that the BGP process loads on the router. And that can be a really frustrating thing to deal with because you're following in your mind all these BGP path selection rules and you're looking at the topology and you're saying, okay, well, it should be taking this particular path, but it doesn't because of how route reflection works. It has to do with how route reflectors actually suppress updates based on where they're learning updates from. So if we go to router 4 and we look at the BGP path to 8. So let's go to router 4. and we look at the BGP path to router 8. Show IP BGP 8.8.8.8. It looks like we're getting this from router 1. That doesn't look... Yeah, I guess that makes sense. We only have one route to this particular destination. And that's the best path, right? For 7.7.7.7, we would go over to router 5. But for 8.8.8.8, we are going over to router 1. Now, if normally we would assume that the reflector would learn about all the paths to the destination. Because there is an alternate path to this destination, which is originating from router 5. If you look at the topology, router 5 can go through AS51 over this external link to router 8 through AS50, but it's not able to do, we're not seeing that in the BGP information. All right, and that's actually normal behavior. It depends on the order that it chooses the route, whether it chooses to advertise that particular route or the other paths onto the other router. The exit path right now is going from router 1 to router 8. Router 8 sent the route to router 1. Router 1 sent the route to router 4. Router 4 reflected that route onto router 5. Let's check router 5 actually too. I want to make sure with router 5 that we're seeing a similar thing. Let's do a show IP BGP for 8.8.8.8. Okay, so now in this particular case, we are learning about two different paths, but this is the interesting part about router 5's perspective, right? Router 5, and this does prove that we do have an alternate path to reach that destination. Which path did we choose? We have two available paths in this case. Path number 1 is the best path, and we have to understand what the reasoning is for that. So if I do a trace route to 8.8.8.8 and I source that from 5.5.5.5, we should see that we're going through the IGP domain to reach that particular destination. All right, so we're going to router 4, we're going to router 2, we're going to router 1, and then we're going over to router 8. All right, that's actually kind of an interesting path. I don't know why we're going to router 2. Let me look at the topology diagram. I guess that makes sense. We could choose to go to router 3, or we could, this is where the ECMP, iBGP ECMP process comes into play. We got some tiebreakers that we're using to decide whether or not we're going to go to router 3 or router 1 or router 2. And that ends up happening to be like the lowest router ID between the two routers. So we could choose this path or we could choose this path because these are equal cost paths from an IGP perspective. But we choose the path to router 2 because of the tiebreaker selection process with BGP. All right. But anyway, we are taking the path through that domain. Now we do see the other path through router 7, but based on the fact that the multi-exit discriminator value doesn't apply here because it's not coming from an eBGP peer. The local preference is the same. Now this is an internal path versus an external path. Normally you would say, well, I normally would choose an external path over an internal path. But in this case, based on the path selection process, AS path attribute is going to be deciding the path prior to using external versus internal. All right. This is an IGP route. This is an IGP route from router 5's perspective. Let me see here. Oops, wrong box. From router 5's perspective, I'm not sure why that's showing up there, but all right. But ultimately, the main reason that we're choosing this particular path, and like I said, we'll get into BGP path selection process a little bit later on, is because of the AS path length. Okay. All right. I'm still kind of thinking in my mind how I want to demonstrate this. The router 5 is learning the update multiple ways. It's learning it with AS50 and 51. Well, it's learning it between the peering relationship between AS50 and 51, and it's learning it via router 1 and AS100. Based on the attribute of the path, in this case, based on the AS path length, we say that the path from 51 to 50 is not valid, and we go through AS100 because that becomes our best path. The end result of this is that router 5 stops advertising the alternate route. And this is what I was really trying to demonstrate, is this becomes one of the disadvantages of route reflection. If the network did need to reconverge, if the link between router 1 and router 8 goes down, for example, router 1 would have to send a withdrawal message saying that the route is no longer valid. Router 4 would then need to withdraw the route to router 5, and then router 5 would need to invalidate the route, install the alternate path, and then advertise the update to router 4. The router 4 reflector would then have to reflect that route back down to the rest of the routers in the IGP domain. All right. That sounds like a lot of work, and it's a very slow process to converge. If it's a full table, it's not going to be quick, right? I mean, we're talking about relatively small databases. We don't have a lot of routes, but if you're talking about 100,000 routes, 200,000 routes, this could be really, really slow. This problem is inherent to route reflection because the route reflector is making the decision on behalf of the rest of the network. They only see the one possible exit point of the network, the other routers that are being reflected the routes. That's why when you go to router 2, you only see the one path. So let's go to router 4 and manipulate the selection process. Okay. In other words, I'm going to change one of the attributes that is used prior to AS path to make the route through the neighbor of router 5 more preferred. All right. I'm trying to think if I want to do this on, I'll probably do this on router 5 actually. Let me try it on router 5. All right. Because you typically local preference is an attribute that you want to propagate into the iBGP domain through a perimeter router that's at the edge of the network. So let's come in here and let's configure a. So essentially what I'm trying to do here, guys, is I'm trying to make it so that router 4 prefers to take this path to reach 8.8.8.8 and see how that influences the other route reflector clients in that process. So I'm going to create a route map, and we'll call this route map local underscore preference, because that's the attribute that we're going to change. We'll set the local preference to 200. All right. This is a higher value than the default. The default is 100. Again, we're going to come back to these attributes in much more detail later, and really kind of get into what the details are of each of the path selection processes. But we will kind of just table that for right now. Let's just say that a local preference, a higher local preference, is going to be preferred over a lower local preference route. And local preference is always selected prior to AS path. All right. So what I'm going to do is I'm going to say when I receive updates from router 7, I'm going to apply that filter, those metrics, if you will, for lack of a better term, to those updates from router 7. And I'm trying to think, this should work. Let me see. I might have to do this on router 4, but I think the attributes get propagated through to the reflector. This will be a good test. So I'm going to go into router BGP 100. Let me do a show run pipe section router. And we're just going to apply this route map to the peering relationship that we have between router 5 and or neighbor 7. Okay. So let's go into, let's say, neighbor. And 172.16.57.7. And I'm going to say route map local underscore preference in. All right. So this doesn't happen automatically. I need to do a soft reset or a hard reset of the peer to reset the routes. Because we don't have a large domain, I'll do a, let me turn off my debugging on router 1. Undebug all. I forgot that was still running. I'm just going to clear the whole thing here, iBGP star, so that I get the routes back from router 7. Now, what should happen in this case is we should be using router 7 to get to those the rest of those external prefixes. So if router 2 in this case wants to get to the 8.8.8.8, we should be following a different egress path in this case. So let's go over to router 2 and do a trace route to 8.8.8.8. We'll source that from 2.2.2.2. Oh, we're still taking. Let me clear. Let me try one more thing on router 4. Clear all the iBGP peering relationships as well. Takes a little bit to converge here. I may have to apply, I doubt it, I shouldn't really have to, but I may have to apply this policy to the route reflector and its relationship to router 5 rather than the external router. Show IP BGP summary. So I'm not getting the external routes at all now. And let's check router 4. Show IP BGP 8.8.8.8. All right. So the attribute is being set for 8.8.8.8, local preference of 200. And previously router 4 was going over to, router 4 was received from route reflector client, so that's router 5. And the AS path is 5150. So it is going to router 7 from router 5. So it is getting learned correctly. If I do a trace route to 8.8.8.8 from 4.4.4.4, we're going to 5 to 7 to 8. Now, why isn't router 2 getting that? I wasn't being patient enough. Okay. So see, we are getting the 200 for the external prefixes. And we are actually preferring to go to router 7 to reach those destinations. So I just wasn't being patient enough. Let's do a trace route to 8.8.8.8, and we'll source that from 2.2.2.2. Going to router 4, router 5, router 7, router 8. All right, so we are able to influence the path selection process, right? We are going to be able to influence the path selection process, but I'm not done yet because I want to show you something else. Basically, we influenced the router. We said in order to exit out, I want to prefer router 5 as the exit point instead of router 8. All right. And how do we do that? We use local preference. Local preference is actually one of the easiest attributes to use because it affects all the peers in the autonomous system. You can normally set it at any point and it will inherently affect anybody, but like I said, you normally kind of establish the local preference values on the edge router in the domain. Okay. You can run into some pretty unpredictable results though when you introduce route reflection into this scenario. We should be learning this path from two different sources. And we're talking about the same prefix, but different points of views in the topology based on where they're appearing and with different ASs, AS50 and AS51. And then on the back end, 50 and 51 are pairing with each other. So normally router 4 would choose one of these as the best path and then advertise the best path on, and typically the alternate egress point would be lost. All right, so let's shut down the link between router 5 and router 7 so that eBGP pairing relationship gets dropped. All right, so show IP interface brief. Config T interface, we're going over to 7 gig 02, and we're just going to shut that interface down. Now, naturally, what should happen, right? We're going to get a withdrawn route. The interface flaps. The routes are going to flap. We're actually going to lose the pairing relationship. That's called BGP fast external fallover. Basically, it's saying, hey, I was paired with you with a connected interface. I'm not going to wait 180 seconds to flap the prefixes because I know you're no longer there. I'm smart enough to know that. So now router 2 should say, I'm going to go ahead and use R1 as the exit point for 8.8.8.8. Let's go over to router 2, do the same trace route, and I'm going over to router 1. So that's good, right? That's normal behavior. We're able to fall over to the external path. All right, now let's bring the link back up. And the BGP update should be relearned. I hope this works. I've thought about this a lot to see if I can get this to work. So let's hope this works. We do a no shut. That'll bring that interface back up and give it a second. Okay, there we go. We got our adjacency. What do you think should happen in this case? All right. What should happen, I mean, logically speaking, based on the fact that we're still pushing local preference, is we should go back, relearn that route, and router 2 should be going back to the original path. All right, let's look at router 5, do show IP BGP. For 8.8.8.8, we only have the one path through router 7. All right. Now, if I look at router 4, show IP BGP, 8.8.8.8, I have the one path also through router 7. So it looks like, let's go check router 2. Looks like we did fall back. All right. This actually wasn't what I wanted to happen, unfortunately. Let me see if I can explain what I was hoping to accomplish. R5 says it should say that it kind of has two different ways to get there. Well, R5 wouldn't, R4 would, right? Because R5 is a route reflector client. It should say I can go through router 7, or I can go to my internal peer, based on the fact that we have route reflector. In the case where we're trying to influence path selection with local preference, it actually should not have worked. And I'm trying to think about why. It may be where I applied the local preference configuration, because there's a particular behavior that I'm trying to create here. It's called, believe it or not, a BGP wedgie. I was trying to think based on our topology how I could actually create this, which is why I moved router 5 into that domain. But it has to do with the order of the process and how it loads. you can end up with a non-deterministic result where you say, I want to do this using local preference, but depending on who advertised the update and who had to withdraw the updates, you may never get advertised that update as an external path to begin with. And I'm trying to think, let me think about this for a minute. I'm going to finish up my other points here. Think about this for a minute and think about how I might be able to duplicate that. I might have to table this and try to duplicate it another way. If you Google BGP wedgie, it's an interesting conversation, but let me look at the topology here. So we brought down this link. Well, we had this link active here. The snipping tool. We had this link active here with a local preference of 200, which influenced the rest of the domain to say, hey, you need to go over to router 5 to get to that particular destination. We brought the link down, which then forced us to install this route here. And maybe I just didn't give it enough time. I thought I tested it so that router 5 would choose to take the path through the route reflector. Now what was supposed to happen is if I'm getting a route from the route reflector, and this is specific to a route reflector configuration, if I'm getting a route from a route reflector, the route reflector is making the decision on what the best path is. I am going to suppress advertising the same route back to the route reflector, even if it may have a better value like a higher local preference or something like that. And I will simply use the route that the route reflector chose. That's what I was trying to demonstrate. That's this concept of a BGP wedgie. It's something that's well known in BGP, particularly with route reflector configurations. It's actually identified in the RFC. I'll pull that up and show you guys that in a little bit. Where you get this non-deterministic routing and it doesn't route the way that you want it to route. The main goal in the case of implementing a route reflector is not reachability, but scalability. We don't necessarily care if we're choosing the best path or the best exit point when we're using route reflectors. If you want to influence specific exits, you may not want to use route reflectors depending on what that physical topology looks like. And I think in this case, I think I'm running into a situation where the physical topology is trumping my goal to show you something a little bit different here. We still got a little bit left to go though, so I'm going to table that for now. If I can try and maybe just demonstrate that a little bit later, I will. All right. There are some other workarounds you could do, of course, where you have two route reflectors with clients that peer on both of them, like router 4 and router 1 could be route reflectors, and then you could see both exit points. If you look at router 2 again, you know that you're not going to see all of those exit points because we're basing our decision based on what router 4 decided. The edge router is going to be learning multiple routes because the external routes are going to be preferred over the internal ones. That's inherently different than an IGP protocol, specifically with route reflector behavior. But this is essentially the design behavior when you're dealing with route reflectors. Route reflectors hide the topology information, and the goal again is to shrink the control plane. Okay, I'm just basically saying, look, I'm going to follow the decision of the route reflector makes, and then I'm going to use my next hop and recursive routing to get out of the network. So I don't necessarily have to go through the route reflector from a data plane perspective, but I'm at least going to trust the exit point decision that the route reflector made to leave the autonomous system. So when you go to modify the path selection, you need to understand why we would be choosing one path over the other and so on. Now, we haven't talked about BGP path selection yet, and let me see if I can. There is a good document to take a look at with regard to BGP path selection, and we're going to take a look at this later on. So if I just do a search on BGP path selection, there is a Cisco document that describes the BGP path selection algorithm. All right, and I don't want to go through this in detail because we are going to see this a little bit later on. But if I go to the path selection process, we can see the different steps. So weight would be the first attribute that we're going to look at. That's a Cisco proprietary attribute. We'll also talk about this concept of transitive and non-transitive attributes, mandatory versus optional attributes, and so on. But you can see local preference is the next attribute, which is why we ended up choosing that external path. Then we have local routes, so I'm going to prefer a path that was locally originated through a network statement or through some sort of route aggregation. Then rather than something that was redistributed. So I'm going to prefer the routes that have an AS path or the routes that have a question mark over something that was learned through an IGP routing process. And then I'm going to finally choose the shortest AS path. Then I'm going to go into selecting the lowest origin type. IGP is lower than EGP. EGP is lower than incomplete. Incomplete would be through some sort of redistribution process as well. Then I'm going to choose the lowest multi-exit discriminator. We'll talk about that attribute a little bit later on. That's an optional non-transitive attribute in BGP. And then I'm going to go through, and there's a whole bunch of tiebreakers here, and then I'm going to choose my eBGP paths over my iBGP paths. I'm going to prefer the path with the lowest IGP metric to the BGP next hop. And then I start to get into kind of a whole bunch of different tiebreakers, right? Who has the lowest router ID? Who has the lowest route, the oldest route? Normally, you don't ever get down to this point. You've already made decisions prior to that. And in our case, that's definitely the case. But even if you have a case where you have multiple equal cost paths with iBGP, you can use multiple exit points and so on. So we'll talk about that a little bit later on. All right. Now, if I go into router 5, based on what we already have configured, I know we're getting a little bit long in the hour here, guys, so I'm going to try and wrap this up pretty quickly. If I go into router 5 and I do a show IP BGP 8.8.8.8, I just want to point out a couple of things. The best route, there's a virtual number. That's the update group number 7 there. That's a virtual number. Doesn't really matter much, but we are sending updates. We are sending updates to that update group. We'll talk about how we can see that. Actually, I can show you that right now. Do show IP BGP update group. So we can see who we're sending this information to, and we can see that we're sending it to our route reflector, right? Router 4 is the only peer that we're sending information to. Actually, we are sending it to our external peer as well. All right, so that's how we kind of identify the update group. It's just a number that allows us to reference which peers we're actually sending it to. Actually, in this case, 8.8.8.8 is only being sent to 4.4.4.4, which makes sense because we're learning about 8.8.8.8 from router 7. Okay, and we choose the best path. We would normally have two choices, but we cannot advertise the route to the router we learned it from, which would be router 7 in this case. Weight doesn't show up in this because weight is 0. The local preference is 200 in this case because we modified that value. And that's actually one thing. Let me do a show IP, show run section BGP. Oops. Sorry about that. Slash router, do show run pipe section router. I was going to take that out because I'm trying to see if we can actually introduce a tiebreaker. I don't think we're going to be able to because we're getting the route from a route reflector. Now, I won't do that for now. All right. In other words, what we're trying to do, and that's kind of what I'm trying to demonstrate here, is that based on this information that we see in the show IP BGP output for that particular prefix, a lot of the information that's stored here is how we're making that decision on which route to choose. So if I did have multiple choices here, I could start comparing those numbers based on the selection process and choose the particular route based on that selection process. We saw that in the very beginning because we were running a full mesh, BGP full mesh. If I do a show IP BGP 5.5.5.5, we can see that this is a local route, and none of these other attributes really are going to matter because we're the one originating that particular route. This is my router ID. All right. So quad 0 simply shows me that this is my route. All right. Now, if you go into RFC 4456. Let me pull that up real quick. This will be kind of the last thing we'll talk about, and then we'll wrap it up. If I go into RFC 4456, I think it is. Yeah, route reflection. And if you look specifically at, I think it's section 10, section 11. Configuration and deployment considerations. They actually talk about this BGP wedgie concept. And they talk about what are some of the considerations, right? We summarize the routes and we only reflect the best path. So that's a key point to this. The route reflector summarizes routing information and only reflects its best path. So that's where we lose that visibility in the topology. The other point here is, let me see. Let me see. May not. Right here. With certain route reflection topologies, the route reflection approach may not yield the same route selection result as that of a full iBGP mesh approach. Okay. And so these are facts that I was trying to demonstrate, but I think our topology is a little bit incorrect for that. All right. The other big thing to think about is the cluster ID, where we have loop prevention with the cluster ID. And it's pretty much the same as originator ID. If I receive a route, or if I get reflected a route with the same cluster ID as mine, I'm going to go ahead and ignore that particular route. All right. So we could demonstrate this, but I think for now I'm just going to kind of table that. Maybe we'll get to a chance to take a look at that a little bit more later on. But just keep in mind, if I was to configure, say, router 2 as a route reflector in this topology, and then I was to peer router 2 to all of the other routers, and using the same cluster ID for redundancy purposes, both R4 and R2 would become clients. And so R2 would be reflecting routes to R4, and R4 would be reflecting routes to R2. But because the cluster ID, which is essentially a value that we can set, we can actually go into the router and set the cluster ID. I can at least show you that. So if I go into router 4 and I say router BGP 100, and let me think about this. What is the command to set the cluster ID? I don't remember it. I forget what this stupid command is to set the cluster ID. I think it's just BGP cluster ID. Let me see if that, cancel that. BGP Yeah, cluster ID. Okay. So we can actually set the cluster ID to a specific format. So for redundancy purposes, I don't have to rely on the router ID becoming the cluster ID. I could actually set the cluster ID to a specific value. This would be for redundancy purposes, right? So what would happen in this particular case is if I did that, and I put all the clients and I make them part of the same cluster, then we kind of change how things get propagated, right? If I had, for example, by the way, the cluster ID does by default come from the router ID. You can actually see the cluster ID by doing show IP BGP cluster IDs. Show IP BGP cluster IDs. And you can see the cluster ID that's configured. So we're doing client-to-client reflection and standard cluster configuration. Okay. If R2 was set with the same configuration, we would see the cluster ID included in the updates, and we would simply ignore them because they would see them included in our own cluster list, our cluster ID list as well. All right. So that's just another loop avoidance mechanism that's built into this particular process. Keep in mind that the cluster list is an inbound filter. It's not an outbound filter, so it won't prevent us from sending redundant information out, but it will allow us to filter redundant information coming in. I mean, ultimately, guys, in the end, it doesn't really matter. BGP is not used to route the traffic. We're still relying on the underlying recursion to resolve the data plane flows in our topology. So even with what we've seen today, and we're going to wrap this up, even with what we've seen today, you can see that it gets rather complicated, right? These are really basic examples. What's the bottom line? If you want the routers to have a maximum view, you want to go with a full mesh. We're going to take a look in our next lesson at confederations. And we'll see with confederations, we end up having essentially the same problem. The last thing I want to mention is what we've already said, which is all of this configuration is based on a per AF configuration. We're going to see more of this when I get into IPv6 and MPLS. But just because you're the route reflector for one topology doesn't mean that you're going to be a route reflector for the other AFI or other SAFI topologies. Okay? All right, guys, we'll wrap it up for this lesson. Hopefully you learned some stuff today. I'll reach out to you guys on our next lesson. I think it was scheduled for tomorrow. We'll see how everybody feels. I'll upload the video tonight. But hopefully that covers a lot of questions that you guys might have on configuring route reflectors. Any questions? All right. We'll see you guys in the next lesson.